Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In my channel, I deal with the different aspects of mathematics, physics, chemistry and biology. So today we are going to look at a concept in calculus, and this basically is the concept of integration. Now in our earlier video that we had done a concept of introduction to calculus, we had said that the concept of calculus basically can be categorized into two broad categories. That is integral and differential calculus. Now, in the concept of differentiation that we have done partly in our first video, we said that basically a differentiation dealt with various problems where we were given a specific function and we were required to find what we refer to as a derivative. And in this particular case, we are going to use this specific concept in order to find the original function. And this basically is going to entail the concept of what we refer to as integration. Now, sorry for that. Now, suppose I have a function f of x from my previous video on differentiation. We say that we can be able to find what we refer to as a derivative of this specific function, which was given as f prime of x, given as such. So in this particular case, I can give an illustrative way of trying to, of course, visualize this particular aspect of differentiation, whereby we're going to have this f of x being transformed through this process of differentiation to another function, which is f prime of x. So we say that this specific operation is referred to as differentiation, and this falls under the category of differential calculus, as I've mentioned. So in today's operation, we're going to perform a particular process that is going to enable us, of course, find the original function. And this process is going to be entailing the concept of integration, which is our subject of discussion for today. So this basically, there are specific terms that we're going to use in reference to these two parts of this specific illustration. Now this one is going to be referred to as, in this specific respect for differentiation, this is a function, and this is going to be referred to as a derivative. Now for integration, this is going to be what we refer to as a derivative, but the reverse process is going to result in what we call an antiderivative. So this antiderivative sometimes is referred to as an integral, and therefore the process of finding these integrals is referred to as the concept of integration. Now there's a specific denotation that we're going to use in reference with this specific concept of integration, and I'm going to just use this specific space. So suppose we have a function f of x, and we were required to find what we refer to as an integral, which is f small of x. Then therefore, of course, this is going to be a function, and this is going to be a derivative. And we said the reverse of this process is going to be, this is a differentiation, and this is integration. So therefore, if we have a function which is basically f of x being given as such, we can define this one as an antiderivative, and therefore we can be able to give that one in form of an equation whereby we're going to have this represented as this is a differentiation of this specific function, which is an antiderivative, going to give us f of x as such. So this is the relationship that is going to exist generally for the derivative and integral, and therefore we can be able to give just a general example. Now suppose we have a function dx of a particular function, or perhaps we can just give it such, or rather another arbitrary letter which is going to assist us make it a subject. So therefore, suppose this specific function is going to yield a derivative on this other side that is going to be 2x. And therefore, if we are required to find this function, we can do a reverse of this differentiation process and pinpoint that this specific function inside here is going to be the square of x. And therefore, we can be able to indicate this one as x squared. The derivative of x squared is going to give us this specific 2x. Now in our case here, then therefore we're going to refer this function as fx is going to be the square of x, and then f of x is going to be 2x. Now in our specific case, therefore this is going to be a function and this is going to be a derivative. Now we have a general illustration, or rather the integral notation that we're going to generally use for various aspects of this process of integration. And I'm just going to write it on the board so that we can be able to do that representation. Now we said that integration basically involves, when we were talking about the concept of an integral in our introduction to calculus, basically we referred an integral as an area that has been bounded by a curve, and we had said that this area under a curve can be referred to as an integral. Now suppose we have boundaries for A and B, and we require to find the area under the curve for this specific case, then therefore we can be able to refer this area as an integral. So basically we had said that one of the ways in which we can find this area is a summation of these little rectangles that are going to be here, and then we said we can be able to use the concept of a summation of these squares of this specific function from A to B by using this specific limit. This is one of the applications of integration whereby we're going to find area under curve, but I'm just going to leave this one as there. But my main emphasis was to try and elaborate on this specific function. Now this is a summation, of course, which is, as we said, is going to be given as an elongated S, especially when we are going to deal with the concept of integration in general. So therefore, if I use this sign, this basically is going to refer to as a summation or an integral. So the integral of f of x dx, then therefore is going to be given as a notation which is going to represent fx plus c, where I said that this is going to be a function or an integral, and this is going to refer to what we call a constant. And we're going to elaborate more on that specific constant whenever we're going to use specific examples. Now in this case, we have different laws which are being used in order to find different integrals. And one of the laws that we're going to see that is a concept that involves a constant. And therefore, we're going to have a specific general formula for trying to find what we call constant integrals. So for the constant integrals rules, it is going to apply for an integration expression which is going to be given as k dx. It's going to be kx plus c. So in this specific case, k represents a constant, and therefore the result for those constant integrals are going to appear in that specific form. Now for other integrals which are going to assume different formats, we're going to have the integral of k of a function fx dx, which is going to be given as k, the integral of fx dx. Now in a sense, this is going to give us a clue that whenever you have a constant, perhaps a numerical constant, then therefore it's going to have this effect. And in this case, some areas, like for the constant multiple rule, we're going to see that this specific constant is going to be taken out of this summation sign, and that is one of the ways in which we're going to deal with what we refer to as a constant multiple rule for integral calculus. Now in this specific case, of course, we can be able to look at the sum and differentiation rule, which is basically going to be a compounded one and trying to create a contrast with the first rules that we have given for a constant and the constant multiple, or rather the multiple constant rule that I've mentioned for the second case. Now this is going to appear in form of a general equation, whereby we're going to have the integral of a function f of x plus or minus g of x. So g of x is going to be another function, which basically is going to appear as either sum of two functions or a difference of two functions. Now this is going to be given as f of x, g of x dx. This is going to be given as the sum of those individual functions. So we're going to have f of x dx plus g of x dx given as such. So basically this implies that whenever we're being given two functions and we're required to find the integral, then it's going to be a sum of those individual of course functions given as such. So the last one we're going to look at is basically what we refer to as the simple power rule. And for the simple power rule, this is going to deal with what we refer to as exponents. And in some way, we're going to expand them and try to see how we can be able to deal with different exponents in various integral functions. So suppose we have the summation over x to power n, and this is with respect to x. So this is going to be given as x n plus 1 over n plus 1. So basically, we're going to raise this specific exponent by 1, and then the result of that is going to form our denominator for that case, and then it's going to be plus a constant. So basically, that's how we are going to deal with the simple integral functions that we're going to come across. So in our next discussion, we're going to use these 4 specific rules and try to tackle specific examples and see how these different rules are going to apply, especially when we're dealing with the concept of integration for the constant integral, constant multiple rule, the sum of the difference rule that we have given, and then lastly, the simple power rule that we have used in our last case for this general representation. So catch us in our next video as we are going to look at these various aspects of the integral calculus. And I'd like to request our members kindly to go to YouTube, search Ernest Sciences and Mathematics TV channel. Check on our description boxes for various videos which are dealing with the different subjects so that they can assist us, of course, create a connection between various areas that we are dealing with in basically integration and differentiation, which are going to be similar concepts. So that is it for now. Bye guys, God bless you.